Welcome to a new series of KBC, which stands for Know the Basics of Circuits. So, in this series of videos, first we'll see Ltspice simulation tool. So, we'll be introducing Ltspice. Okay, these are the prerequisites. So, you should be knowing Ohm's law, Kirchhoff voltage law, and Kirchhoff current law. And of course, you should be knowing basic circuit analysis of writing loop equations, nodal voltage equations, and all those stuff. Okay, these are some prerequisites before we start this video. So let us take this circuit and let us try to analyze this circuit using Ltspice. And let us take the values of we have 5 resistors, so let us assume that this is 1 kilo ohm and this is like okay 3 kilo ohm, this is like okay 220 ohms, and let us take this as 100 ohm, let us take it as 4.7 kilo ohm. So these are let me just take it as 3.3k, which are the standard values of resistance. So we shall try to find out, so what is this loop current. So we have a loop current, this is loop current I1 and this is loop current I2. Since these two are the loop currents, I can certainly find out what is this branch current. So this branch current is same as this loop current, which will be I1. This branch current will be same as this loop current I2, whereas the current flowing through this branch is actually I1 is this way and I2 is going this way, so it's actually I1 minus I2 is the branch current. So these are the branches and this is a loop. So loop is one, you start from any node, you have to come back to same node. So branches between two different nodes, so have these two nodes now, this and this. So what are the current flowing through that? This and this is the branch, and what is the current flowing through this? So let me name this as V1 and let me name this as V2 as the node voltages. So let us go to Ltspice and try to rig up the same circuit. Okay, let me take Ltspice. Okay, give me a minute. There are two folders opened. Okay, this is Ltspice. Okay, this is my Ltspice. Okay, now let me take a new draft and let me save it as okay, save as this is circuit 1. Now let us try to spend some time with each of the icon. Of course, these are all very general one, and this is a configure analysis. This is a very important tab in your Ltspice, which specifies what type of analysis you have to do. So there are different analysis. Maybe we'll come back to this particular okay, tab okay a bit late, because let us try to understand the very basic one. And of course, we know that this is for making windows vertically split, and this is for horizontally splitting the windows, and this is cascaded. This is for zoom in, zoom out, and fit to scale. And of course, this is for drawing the wires, and this is for creating ground, and this is for getting a voltage source. You can see these are very basic components that will be used in circuits, so that's why they've been put as these okay bullets, so that you can easily click on this and get the voltage supply, click on this and get a resistor, click on this and get a capacitor. You can also see whenever you go there, so there is a ground in bracket G. So G is like a okay, shortcut key. So if you type G in your keypad, you'll get ground. So similarly for wire, you can see W. Whenever you want to wire something, if you type W, you'll get a wire. Then see here, this is your inductor, this is diode D, and this is okay. Here these are all the component, meaning all components. It's like a library for your Ltspice. If you click on this, you can see all components that are listed over here. This is a folder where you're going to have all components starting from, so very basic, okay, power supply, this is your capacitor, this is oh, of course you can see the description of that. Also you can see current control switch, so in a particular operation you'll end up with this. So you can see you have NPN transistor, okay, you can see there's a bipolar, of course you can see the description here, a bipolar NPN transistor, you can see there is a bipolar PNP transistor, and can you see there is a PMOS transistor, there is a PMOS transistor, there is a Zener, a diode. You can also see there is a diode also there available. You can see, of course, here also you have a diode. Here also you have a diode. You can see there is a diode here. So where is diode? This is the diode. You can see this is description is your is there here, and then so once you select a component, you can simply place. So let me take a resistor. What is this resistor 2? Resistor 2 is, of course, it is both are having same function. So let me say this is resistor. I can just place it. So since it whenever you click on R, it will come vertically, but as per my circuit it is horizontally placed. So for that you can say control R. Control R will make the component to rotate by 90 degree. See, it is there placed, and I need to have, okay, R2 is actually in this direction, and then I have, of course you can see it is incrementing by 1 for after every placement. So I have this, and then I have this as my, so once you place all the components, you can simply say escape, component will go off. See, this is the circuit what I have. See, this is R1, R2, R3, R4, R5. So now I want to have a battery also. So of course you can simply type P. P is a shortcut key for going to components. So you can see here, this is component. You cannot type C because C is already allocated for capacitor. So for component, getting component library, you have to go to P. So P, what I want is battery. So where is battery? So battery is available in this miscellaneous. Can you see there is a battery? You can click on this, you got the battery. Only one battery is enough. Let me just escape this. Now I'm ready with all the components that are necessary to, of course you can see this is my circuit, what I have, and I have placed all the components here. Let me also place the ground here. So let me put a ground also at the bottom somewhere here. Now, okay, you can say again escape. So now all the components are placed, but you're not seeing all of them in a single, it's not fitting to the screen. So what you can do, you can do this. You can see this is zoom to fit. You can simply say, of course, even if you put this space bar in your keypad, it will be, it's like, okay, that's why you can see whenever you come over here, can you see that there is a zoom fit in bracket space. So there's a space key. If you press on that space key, all the components will fit to the screen. Now I can do the wiring. So wiring can be done using this. So you can simply type W in your keypad, the wire will come. Now you can see start wiring. You start from here, click on this, and then stop wherever you want to make a turn, and then click there, and then you again, of course you can simply go through this, you can see this is, I'm just going through this, stop there, again go down, stop here, rotate, and then go down. Then now you can see you can again click and you can go up. Even though it is, now you can see even though it has simply a pass through this, so this wire will be get deleted by itself. And then let me start from here. Let me go down till this point. One thing you can see, this is not connected at all. If it is not connected, you will not see a dot. Can you see there is a connection here? There is a dot. I need to have a dot here. I need to have a dot here. How to have a dot? So what you can do is you can really redo that connection, or you put one extra wire. So I'm just clicking there and then stopping it here. Can you see? So there's a dot created. So you can just repeat that. So while doing yourself in your simulator, make sure that you should have a dot here. If there is no dot, means this ground is not connected to this line at all. So it will be connected to only R3. So let me change the values of the resistance. Then since the connection is done, you can escape, the wire will go off. Now it is time to edit the values of resistor. Again, you can say space bar, it will fit. So this we are expecting the value to be 1 kilo ohm. It is 1k. So no need to write it as ohm, whether it is small k or capital K, it is kilo. It is kilo. So no need to type capital K, even small k is also fine. And R2 happens to be in our design, it is 3.3k, and this happens to be 220 ohm. So no need to specify it as ohm, just 220 is indication of. So now this is 100 ohm, and this is 4.7k, 4.7k. Or let me just make it okay, let me make it 4.7. Okay, if you, okay, let me just go back to my circuit and slightly change this to 4.7 mega ohms. So this is mega ohm. So if you want to put mega ohm in this simulator, it is 4.7, not capital M. So capital M means milli, small m also means milli. If you want to specify mega, it is MEG. So it is now 4.7 mega ohms. You can see this is either it is small letter, capital letter, doesn't matter. Now this is mega, this is kilo, this is ohms. Fine. So now let me specify this as 5 volts. So I'm done with the circuit connection. So this is we are done with circuit connection. So if we just go back and see what the circuit is, this is a circuit what we expected. So we wanted 1k, this is this and this. So let us try to simulate this and try to find out what is of course you can actually find out what is. I leave it to you as an assignment like thing. So what is the current flowing through this? So for that you need to put these two in series, and then these two are in series, they will become in parallel, and that will in turn come in series with this. So I can replace this by something like this. Now this is now 3.52 kilo ohm, and this is like this is 4.7 mega plus 4.7 exponential 6 plus 100. So it will be 4.700.1. Okay, let me just take out this. So this is kilo ohm. So this will become 4.7001 mega ohms. Mega ohms, and this is like this, correct? If you want to know what is the current, this current I. So this current I1 is, then these two will come in parallel. So what is parallel combination of 3.52 exponential of 3 inverse plus 4.7001 exponential 6 inverse equals inverse equals. So the equivalent resistance what you have is, this is the equivalent resistance, which is 3.517366 kilo ohms, and this is 1 kilo. This is 1 kilo. So now what is the overall resistance? So this is 5 volt, and overall resistance is of course this current I1 would be equal to 5 volt by 4.51736. So I'll make this plus 1 exponential 3, 1 over that into 5 would be a current of 1.106 milliamperes. Milliamperes is the current that is flowing through this I1, or this one. So of course later, so now here we're not going to verify anything, so we just want to use Ltspice. Maybe in the later version we'll just try to verify the things. So we should get a current of 1.106 milliamperes. How to verify this? So there are now I need to simulate. So in order to simulate, so we have to come to this circuit analysis, because we need to do the analysis of the circuit. So analysis of the circuit means, so you should measure all nodal voltages and branch currents, and you may also try to know what is the time response of the circuit, frequency response of the circuit, all those stuff. So that will be specified in this setup. So this is what is transient, and you can do a transient whenever you are doing some signal analysis is there, you're giving some signal and observing the output voltage. And otherwise you can see this DC operating point. So this DC operating point will compute the DC operating point, treating capacitances as open circuit and inductors as short circuit. Of course, for this, in this circuit, neither we have a capacitor nor we have an inductor. So since we have only resistors, so these opening of capacitors and shorting of the inductors will not happen. So if I say this, I can place this and then simply run this. Now you can see it is giving all voltages and currents. You can see now this is voltage N002, N001, N004, N003. So what is this N001, 2, 3, 4? So how do we understand this one? Okay, of course this is a bit thing which you're now looking at. Okay, how do we know okay, which is N1, which is node number 1, 2, 3, 4, and that we just try to see in just a minute. So you can just see what are the currents flowing in different branches, that is different components. It is I of R1. Can you see I of R1 is minus of, this is the current. So we were looking at this is the current. Now what we are looking at is this current. We were actually looking at 1.106 milliamperes. It's the current flowing through R1. So are we getting that? You can see you're having that. So it is 1.10. So this is actually in amperes. If you convert to milliamperes, it will become 1.10684 milliamperes. So this is the current. You may be wondering, okay, why this current is negative? Some currents are negative, some currents are positive. It is only because the way how you place the component. I can make this negative current positive, I can make this positive current negative by rotating the component. So what I'll do is I will select this component. How do I select the component? Can you see there is something called as move? Just click on this, just hold this. Let me simply say rotate. Control R twice. Let me place it now. If I run it now, you can say escape. If I run it now, this current will be now positive. You can see. Can you see the current is positive? Can you see I of R1 is, earlier it was negative, now it is coming like positive. Correct? And here also you can see wherever you have this negative current, simply, of course, if you want to don't be get confused that okay, this negative current is the answer. Actually the current flowing in this R2 is actually going in this direction. Suppose if I rotate this resistor R2 and R3 by 180 degree, you'll get that current as positive. So what I'll do, let me again this is, you have to select. For selecting, you say it as move, that is M. Click on this, control R. I'm just placing it back here. Again, I'm moving this control R. I'm just placing it here. Now if I run, see all the currents are positive. Can you see these currents are positive? And why this current is negative? This current is negative here because whatever current that is entering, so this is I of v1 is whatever, why it is negative means it actually indicates what is the current entering the node positive. So let me just show you here. So what does your Ltspice will always give you is, it is actually giving the current which is entering this positive node. You can see whatever the current that is entering is exactly the opposite of current that is this I1. If you can carefully notice, I of V1 is nothing but current entering positive node of positive terminal of the supply. So that's why that current is negative. Actually current is not going in this direction, current is actually going out of the source. So that's why this current is negative. So this magnitude is same as the magnitude of I1 except the symbol. Can you see this? I of V1 is exactly same as that of I of R1 except that sign change. Because as we saw in this diagram, so whatever current that you are seeing here, whatever current that is going here, the same current is flowing in the opposite direction, right? So that's how we know what is this voltages through, sorry, current through each of the component. It is interesting to see. Of course you can verify Kirchhoff current law, all those stuff. What does your Kirchhoff current law says? Voltage at any node is algebraically zero, meaning current entering the node is equal to current leaving the node. Suppose if you want to write the current entering the node for this is the node what I have. So current entering the node is I1, current leaving the node is equal to, okay, if I say this as I3, if I say it as I3 plus I2. So this can I write it as, this is I of R1 is equal to I of R2 plus I of R, we have named it as I2, so this is I of R4. So this current is always equal to this plus this, so that's what your Kirchhoff current lies. You can actually find out this will be 1.106 milliamperes. You can find this I of R2. How much is I of R2? I of R2 is 1.10601, and the other current is I of R4 is it's actually 8.28 e power minus 7. So it actually comes out to be, so 1.1060608. This is milliampere, and this, okay, this is what? So you have 1.10601 exponential minus of 3 plus of 8.28 exponential of minus 7. That comes out to be this. So this is these many milliamperes. See here, this is what is IR1. This is addition of, this is actually this, even though this is 8.28, this is e power minus 7, this is e power minus 3. So if you add this actually fits here. So this is actually this 1.108. So this is, if you take the fourth decimal, it is fourth decimal is this. So that's why it is 1.1068, 1.1068. Correct? Now that's how we can measure the things. And let us try to understand what are these voltages V, N001, N002. Basically, whenever we write any circuit now, whenever we write any circuit, let me just rewrite this circuit here. Let me just give you an idea. So this is the circuit what we had. So this is this is R1, this is R4, this is R5, this is R2, this is R3, and the value of this is 1k, this is 3.3k, this is 220 ohm, this is 100 ohm, This is 4.7 mega ohm. Okay, maybe while writing in the circuit we write it as capital M. This is mega, but while writing in Ltspice it has to be MEG. This is 5 volt. This is named as V1, so on so. Correct. So let us see. Whenever we write this spice code, no, okay, I said that this is Ltspice. So let us try to define what is this Ltspice is. Ltspice. So Ltspice is one of the spice programming, spice simulator. So let me just tell you what is this is. So Ltspice is one of the spice programming. So what is this spice? It is simulation program with program with integrated circuit emphasis. So from this simulation program integrated circuit emphasis, simulation program with integrated circuit emphasis, this spice has been derived out of. This is how spice is coming from. Even though it is a simulation programming, so this Ltspice is a graphical interface. Of course, we are not writing any code here. We are not writing any program here to do the circuit analysis, but we are writing this circuit diagram. This circuit diagram will be converted into a program before it start doing the analysis. So this conversion from circuit to program will be done within this Ltspice simulator. Let us try to see what is this program for this circuit. For this circuit, we say it as netlist. So there is a netlist program. There is a netlist program will be written for each and every graphical circuit that you're going to draw it on the simulator. So we will see that what is this netlist program is for this particular circuit. Now for that you can go to this view. Can you see there is a spice netlist? There is a spice netlist. Click on this. Can you see you have this is the netlist, this is the program, this is the program what we are having. So let me let me keep this aside and let me try to understand how does this. Okay, let me take this also with me. See now you have register R1, you have register R2, you have register R2, you have register R3, you have register R4, you have register R5. Now this resistor R1 is, of course you have a voltage source V1 also. Can you see there is a V1 source? Can you see there is a V1 source, there is a R1, R2, R3. Can you see these are all N001, N003, so on so. What does this N001 and N002 indicates? So that indicates where does this resistor is connected between, because we know that this resistor has two ends, this and this. So this end and this end, where it is connected between, it is connected between 1 and 2. This is actually node number. How to name the node is always, this is node number 0. Node number 0 is always this, and you can see voltage V1 is connected between 0 and 1. So what does this first node indicates? It always indicates the positive terminal of the battery. It is now N001. So this is the first the positive terminal of your battery, which is connected between N001. Can you see this is 0 now? That is 0th node here. That is 0th node. See here, this is 0. So where is V1 between? V1 is between N001 and 0. So this is positive terminal, this is negative terminal of the battery. Correct? Then where does R1 is connected between? As per this, because this naming of this as this is always 0 because ground is always treated as node number 0. This is node number 1 and this is N002. This allocation will be done automatically by the system, so user doesn't have any control on this. And since R2 is this, so you can see R2 is between 2 and 4, so this is actually N004, and R4 is between 2 and 3, this is between 2 and 3, so this is N003. And okay, this is how, so R5 is between N003 and ground, and R3 is between N004 and ground. So this is how the node is allocated. See now, where is R1 between? R1 is between N001 and N002. Where is R2 is between? R2 is between N002 and N004. Where is R3 is between? It is N004 and 0. Where is R4 is between? N002 and N003. And where is R5 between? It is N003 and 0. So this is how the connection is done. Without this, if I have this, I can able to write the circuit diagram. So now you need to name this as ground node. This is N001, this is N002, this is N003, this is N004. What does it says? Between 1 and 0 you have a voltage supply, so this is between 1 and 0. Between 1 and 2 you have R1. Between 2 and 3, between 2 and 3 you have R4. This is R1, this is R4. Between 2 and 4 you have, this is R2. Between 4 and 0 you have R3. Between what is this? This 3 and this R5 is between 3 and 0. So between, this is N003 and this is 0. So this is R5. So this is how we have constructed the circuit diagram looking into the netlist. So this is called as netlist. This is called as netlist. So we have written the circuit diagram looking into the netlist. Actually, what does the Ltspice will do is, we have written the circuit, it has created the netlist. We have written the circuit, it has created the netlist. For this network, for this netlist, it will do an analysis. The analysis that will be done is .op. .op, which is nothing but DC current and voltage analysis. So it will measure, it will indicate all voltage and currents through each of the component and at each node point. So it will indicate what the voltage at this node, this node, this node, and this node, all 4 nodes. So okay, this is there, this is there, this is there, this is there. So that's what is these nodes. So what I will measure now is fine. So we will see again the netlist once again. You can see there is one more value here. This is the component name, the nodes between which that resistor is connected, and this is the value of the resistor. You can see R1 is 1K, R2 is 3.3K, and R3 is 220 ohm. This is what we have edited there while writing the circuit diagram. This is what is being uh, realized here, or being what taken here for analysis. Can you see there is a 4.7 MEG, 4.7 mega. Can you see next it is .op, what type of analysis you are doing, and then of course this is okay, start and end of your programming. And if you see this where is this output log, of course it just indicates how much time it is taking, all those stuff. If I run it now, what all things you have? Can you see there are how many nodes are there? Except ground you have 5 nodes, sorry, including ground there are 5. Other than ground you have N001, N002, N003 and N004. So as I said, it will show it will show all it will show all nodal voltages N001, N002, N004, N003. It will actually show all the voltages. So where is that voltages available? All the voltages are available in this. Whenever you do .op, it will list out all. These are all node voltages at each and every node. So how do you name the node? Node naming is not done by you. Node naming is done by the system itself. So this node I don't know. If you want to know what is a node number, you may have to go back to netlist and try to find out where is this R1 is connected between. So R1 is between this and this. You need to see where this V1 is connected. It is between ground and this. So this common thing is this. Now in a big circuit, it becomes very important to know the nodes for which you can label the node. So what I'll do is I will label each of the node. I will name it as input. Let me say this is my node input. Let me name this as node, maybe some, let me name it as some Vx. So this is my node Vx, and I want to name this as Vy. So let me name it as Vy, and let me name this as some Vz. This is Vz. So now what I'm trying to do is, I was having a confusion, where is this N001, N002, all those things. Now that is now totally eliminated. Now this node is input node, this node is Vx node, this node is X node, this node is Y node, this node is Z node. Now where is R1 connected between input and X node? Where is this R2 connected between X node and Y node? Where is this R3 connected between? It is between Y and ground node. Where is this R4 connected between X and Z? Where is this R5 connected between Z and ground node? That you can see here. Can you see here? What I'll do, I will save this and go to view and see this netlist. Can you see that has been totally changed? Can you see this is between input and Vx? It is between Vx and Vy. No, there is no N001, N002. Since the user has specified the nodes as X, okay, Vx, Vy and Vz, all those stuff. So that's why it is now being named as Vx, Vy. Of course, you can give anything. You can give it as ABCD, you can give it as your name, you can give it as whatever you wish. Now, this is how you can, that's why this is called as labeling a node. So that's why it is set as, can you see label net? Every net, that is in your netlist, you are getting it as N001, N002 now. So that is now replaced by Vx, Vy, Vz input and all those stuff. So now if you want to, can you see this is also in terms of that input Vx, Vy, Vz. Earlier it was in terms of V of N001, V of N002. We were totally amazed with, okay, which is this N001, N002. Now there is no confusion. You can easily know what are the voltages. So this is how, using this netlist, you can able to label any net of your interest. It's not required in all the cases. If you want to know what is the voltage at a particular point during analysis, instead of searching for what is that node number, you can actually label that node or label the net, and then you can see for that voltage exclusively there. Suppose if you want to know what is the voltage across R2, what is this? It's actually Vx minus of Vy. It is voltage at Vx is from here to ground. Okay, let me once again clarify. This Vx voltage or V of Vx is nothing but voltage at X node with respect to ground. So voltage at this point with respect to ground is Vy. So all these are called as single-ended voltages. So what do you mean by single-ended voltage? Whenever I say this as, okay, this was named as input, This was named as Vx, this was named as Vy, this was named as Vz. So we got it as V of Vx, V of Vy. So what is this V of Vx? It's the voltage measured at this point. While measuring voltage, I need to have some reference, no? The reference is ground. So that's why this voltage is Vx, this voltage is Vy, this voltage is input, this voltage is Vz. So all these are called as single-ended voltages. Single-ended voltage, meaning if the reference is ground, all measured voltages are called as single-ended voltage. Suppose if you want to know what is V of R4, voltage across R4, that is nothing but V of Vx minus V of Vz. It is voltage across these two nodes is nothing but VR4, which I'll call it as differential voltage. Differential voltage. Because the voltage that is measured is between two nodes. It is not with respect to ground. It is between these two nodes. If the one of the node is not ground, then it is called as differential voltage. If one of the ground with respect to which you are measuring, then that is called as single-ended. What is the difference between single-ended and differential? In case of single-ended, because you always need this plus minus, you need to have two terminals to measure the voltage. If this is ground, if you are measuring with respect to ground, then that is single-ended. If these two are exclusively, if none of them are ground, suppose if this negative is different, this is negative, this is positive, then it is called as differential voltage. If this is the voltage required, it is the differential voltage, which is nothing but V of Vx minus V of Vz. That's how we can measure the voltage across this resistor R4. What is resistor? Okay, R5 voltage, it's N003 or V of Vz is the voltage across R5 or voltage at node Vz or N003. Okay, let us again go back to this. So this is about what .op. So now I can also do one more analysis called as transient analysis. So for that I can go to this, say this is now transient. Now I have applied a DC voltage. I want to see how does the circuit is behaving with respect to time. You can just give it as 1 millisecond. That's enough. Okay, you can start saving the data from initially 0. Even if you don't specify these things, it doesn't matter. Give it as for every 1 microsecond, let it simulate let it give the values. So if the moment I use this, you can see this has become blue. Blue indicates it's a comment. This is now black. Now this is invoked. This is put in what? This is not considered. This is now become a text. So suppose if you just go back and if you click on this, can you see the moment I click on this, and if I say okay, this will become blue, this will become black. Can you see it? Can you see that? This change over. If it is blue means it's a text. If it is black means it's a analysis. It's dot op means you are doing a dot op means DC analysis. Dot tran means transient analysis. Now it is blue means you are commenting this. You are commenting in this. If you want to do transient, click on this, select this transient, say OK. Now this is black, this is blue. Now you can see a transient analysis. Now let me run. Because what does this say? It is start saving data from 0. It will go up to 1. It will simulate up to 1 millisecond and it will show me the result. See now the result is from 0 to 1 millisecond. So this is the time that what we have set in your. So now I want to know what is this voltage, input voltage. You can see the moment I just come on to, okay, once I run this and if I just come on to this, there is a probe coming. Earlier, if this was not there, when I come here, there is no probe coming. When does probe comes? The probe comes only when you're observing something, when the simulation is running. You can see now I'll simulate it. Now if I go to circuit, can you see there is the moment when I come close to a node, a uh, red probe will come. So that is when you go to a particular node. Now what does this? If I click on this, I will get the voltage at that node with respect to ground. You can see this is, see the V of input. It is the voltage at input node. If you click on this, I will get the voltage at Vx node. Can you see? This is Vx. You can change the color of this. You can see default color is blue. You can change it to something else. You can see now this is fine. Okay, it's the voltage at Vx. If you want to know what is the voltage at this point, again come and click on this. See now that is Vz. It's here. What is the voltage at this point? It's again, this is, so what are these voltages? These are the voltages at that node, at that net with respect to ground, correct? Now if you want to measure voltage across R4, so then you have to go there, right click, and then can you see this is keep coming, so that is red. Now this is black. I will keep it here. Can you see now? This is, can you see this is V of Vx minus Vz. So this voltage is actually 82.696 microvolt. You have a very small voltage that is there across this R4. Shall I measure what the voltage across this R2? Okay, if you want to know the voltage across R2, click on there and then come and place it here. See now? This is would mean Vx and Vy. Can you see this is Vx and Vy? This one. Can you see this is Vx and Vy? Can you see this is Vx and Vy? Of course, this is, of course, both are on Vx and Vy. Can you see this is 3.64 volts? So it is the differential voltage. See now, V of input, V of X, V of Z, V of Y, they are all single-ended voltages. Whereas this V of Vx minus Vz is a differential voltage. V of Vx minus Vy is a differential voltage. See now? Correct? So now, if you want to measure, if you want to know this voltage and this voltage simultaneously, what you can do? You can first double click on this input. Now both the cursors are on V of input, V of input. So once you double click on this, both the cursors are on this. You click on Vx once. If you click on Vx once, can you see one of the voltage is Vx, the other voltage is on Vin. So this is what is cursor 1 is Vx voltage, cursor 2 is V input. See here, this is what cursor 1, which is cursor 2. You can see this is cursor 1, this is cursor 1. Can you see this is cursor 2? What is cursor 2 indicating? It's indicating 5 volt. What is cursor 1 indicating? It's indicating 3.893 volts. So this is cursor 1, cursor 2. And what does this indicate? This indicate at what time you are measuring. So this is corresponding to 653 microsecond here, and this corresponds to 365 microsecond. You can see the moment I change this, only x-axis is changing. There is no change in y-axis at all for this particular cursor, because this is your second cursor. When I'm moving this, just have a look at this cursor second and only this horizontal. This line remains there, no? So that's why there's no change. There's not change. Okay, this is about okay, if you want to delete any cursor here, sorry, any of course, to delete the cursors, say it as escape. To delete the traces, we can just delete the trace here, delete the trace, delete, or you can delete all the traces. You can add the trace and delete the trace. You can see here, what do you have? Okay, you don't have, you can add the traces from this. You can add current through. You can add current. You can see now the currents are, because this is voltage, because voltage and current are different parameters, they will come on different palettes. Okay, now this is your current. You can see this is current I1, and maybe if you want to measure Vx and I1 or I of R1, what you can do, you can double click on both, then you can click once here. Can you see one is Vx, other is current through R1. This indicates what is the voltage at Vx node, and this is the current through R1, current through R1 resistor. So of course, if you want to see simultaneously here, you can just do this so that you know where is this is Vx, voltage at this point with respect to ground, and this is the current flowing through this. We can also see the current. Can you see here, if you are going there, this is a probe will come. If you go into the component, can you see this comes, this is the current entering the node R1 from left to right. Here can you see now, this is the current going down through R2, this is the current going down to R3, this is the current that is entering R2 from left to right, this is the current that is going down through R5. So if I click on this, I will get I of R5. See here, if I click on this, of course once if this symbol is coming, if I click on now, I will get IR4. Can you see I got IR4? So in my circuit, whenever I do simulation, I can name the nets to my requirement for my analysis, and I can just make sure that uh, measure the voltage. It can be single-ended voltage or it can be differential voltage also. So what do you mean by differential? It is across the terminal, across the device, across the component. You can see we just measured it across R1. So what is the voltage across R1? It is V of input minus V of Vx, or you can do it like this. This is one is plus, other is minus. You can see that's what is this here. So it is, this is what you can see, this is V of input minus Vx. So that voltage is 1.10 volts. Okay, that's it for the day. Hope okay. Okay, maybe what I'll do is I just give you a small exercise so that you can able to do it, just to have. So let me just take you can just think of some circuit like this. Okay, you can think of something here. There's no need to practical, okay, theoretically verify, just to have a fun of control on your. This is V1, this is V2. Let us name it as R1, R2, R3, R4, R5, R6, R7. Let us have R1 to R7, all registered as 1 kilo ohm, and let us take V1 as 10 volt and V2 as 3 volt. So let us try to measure what is I of all currents and all nodal voltages. So this is ground. How many nodes you're going to have? You're going to have a node. Okay, you can name it as this is X node, Y node. This is maybe Z node, or let me say it as A. This is B. This is C. This is D. This is E, and this is F. A, B, C, D, E, F. These are the nodes. So try to know what is V of A to V of F, and what is I of R1 to I of R7. Just have a look at it and try to write a netlist. Try to write a netlist. So where is this V1 is connected between? It is between A and 0 with 10 volt. So what is V2 is between? It is between F and 0. This is of 3 volt. This is not there. Where is R1 is between? It is A and B. Its value is 1K. Where is R2 is between? R2 is between A and, oh sorry, these two are same. So you can, because there are no component in between this, so there is no E node. So there is only, okay, you can just have, okay, this is not there. So you have only up to, let me name it as E. This is E. So this is only E. Fine. This node is not there because you cannot have without because this node voltage is same as this node voltage, you cannot name it by 2. So these two are same points. So R2 is between A and C, it's a 1K value, and R3 is between C and B, its value is 1K. Likewise, you just write it once, see it in your simulator, what is your netlist program, do .op, do .tran. So just it's a funny what exercise you can think of doing it, so that you know how to write a netlist program, and how to, of course, you written a circuit diagram, you're writing a netlist program for this, and this is what is generated for analysis in your Ltspice. So in some simulators, like okay, high-end simulators like okay Hspice and all those things, there you are supposed to write this type of netlist need to be written for describing the circuit. I'm actually describing the circuit here. So this is my circuit, I'm describing where the circuit is, how the circuit is connected. So this is what is my description. So that is there in bit high level spice tools. This Ltspice is a graphic interface where you're writing a graphic. That graphic interface will create a netlist for you, and the simulator will do the analysis. In this type of bit high-end simulators, where they won't accept this type of graphical this one, so you are supposed to write a netlist for that circuit to so that it can straight away start the simulation. So this writing netlist is an interesting parameter or interesting exercise for a given circuit, so that you can use, you can write a netlist for any given circuit diagram. Thank you.